I will cover this topic under the following heads: introduction, the phase rule, simplifying components, metamorphic phase diagram, ACF diagram, method of calculation of ACF, ACF values of some common minerals, and lastly the conclusion. Like igneous rocks, metamorphic rocks are also composed of 9 or more major elements like SiO2, Al2O3, Fe2O3, FeO, MgO, MnO, CaO, Na2O, K2O and H2O. Thus, initially it would appear that we are leading with a 9 or 10 components system. However, the number of components in any given system is the minimum number required to define the composition of all phases in the system. Thus, since constituents like Na2O and K2O are not usually found as a separate minerals phases, we can combine these with other constituents like Al2O3 and SiO2 in the feldspar like albite and orthoclase, and thus reduce the number of components required to define our system Na2O plus K2O as alkalis. This is important if we graphically display chemical rocks and mineral data in a way that is easily visualized. In fact, the best way to visualize such data is to attempt to reduce the number of components to 3, so that we can plot the composition of the rock and minerals on a triangular compositional diagram. Before discussing how this is done, we first review some of the principles of 3 components compositional diagrams. The phase rule, Gibbs 1982, phases, distinct materials or states plus degree of freedom, independent variables equal to components plus 2. Now, the next module is degree of freedom, pressure, temperature, pH2O, pCO2, pH, oxygen phygosity, EH, simplifying degree of freedom. Generally, we ignore pH, EH, oxygen phygosity for most rocks important for sulfide system. Usually care about pressure, temperature, assume PS2 equal to P total for silicates, PCO2 equal to 0, assume PCO2 equal to P total for carbonates, PS2O equal to 0, assume PS2O equal to 0 and PCO2 equal to 0 in some cases. Therefore, P plus F equal to C plus 2. If degree of freedom equal to 2, then P equal to C. Phases equal to components. Number of phases equal to number of components. Components equal to SiO2, Al2O3, Fe2O3, FeO, CaO, MgO, Na2O, K2O, TiO2, Cr2O3, MnO, BaO, SrO, P2O5, H2O, CO2, fluorine, chlorine. We can plot a maximum of 3 components using triangular diagrams. Ignore SiO2 axis, water axis or 0, CO2 axis or 0, assuming P2O5 goes into apatite, Na2 into albite, TiO2 into rutile or ilmenite, Cr2O3 into chromite, F into fluorine, fluorite or apatite, chlorine into halite, includes MnO with FeO, barium oxide and strontium oxide with calcium oxide, Fe2O3 with Al2O3 or FeO, Cl, fluorine with OH. Subtract major elements as necessary. Components reduced to Al2O3, FeO, CO, MgO, Na2O, K2O, ACF graphs Al2O3, CO, FeO plus MgO, AKF graphs Al2O3, FeO plus MgO and K2O, AFM graph Al2O3, FeO, MgO, K2O in a tetrahedron SiO2 CO MgO used for carbonate system. Plots molar amount, not weight. Tie lines denotes two coexisting phases. Triangular subfields denotes three coexisting phases. Phase diagram is given the idea about the mineral combinations under given pressure temperature conditions. Evolution tracked by changes in diagrams. Normally F equal to 2, C equal to 3, P equal to 3. On a reaction curve, F equal to 1, P equal to 4. How to get 4 phases together? New phase appear in middle of field, new phase appear on tie lines, tie line break and new one form. Changes in metamorphism, new mineral appear, old minerals disappear, and compatibility shift towards stability diagrams. ACF diagrams. Ascola in 1915 proposed the ACF diagram as a way to illustrate metamorphic minerals assemblage on a simplified 3-component triangular diagram. He concentrated only on the mineral that appear or disappear during metamorphism and also give idea about the grade of metamorphism. The chemical composition of rocks and silicate minerals is convincingly stated in terms of 10 main oxides, namely SiO2, Al2O3, Fe2O3, FeO, MgO, CO, Na2O, K2O, MnO and H2O. It is impossible to represent graphically all possible variable in the mineralogy with a broad system of more than 3 or 4 components. Therefore, it is necessary to reduce the number of components for graphic representation. In common metamorphic rocks, SiO2 is present in excess, that is, quartz is constituents of many metamorphic rocks, and thus only those minerals with highest possible SiO2 content can be formed. Consequently, the amount of SiO2 has no influence on the mineral assemblages and thus need not be represented graphically. H2O may be considered as mobile component and thus may not be considered for calculation. Similarly, Na2O and K2O may also be neglected because rocks containing alkalis may have albite and potash feldspar as additional phases. Besides those shown in the diagram as biotite and muscovite also contain K2O. Therefore, a separate AKF used to represent the mineral assemblages and containing these micas. Thus, it is possible to reduce the components as follows: Al2O3 plus Fe2O3, because Fe plus 3 substitutes Al plus 3. Second, FeO plus MgO plus MnO, these can be combined together because MgO and MnO commonly substitutes FeO in silicate minerals. And third, CaO as independent. The above three components are used by Ascola to represent the mineral assemblages of metamorphic rocks of the different phases. Method of calculation for ACF values. First, weight percent of Al2O3, FeO, MgO, MnO, Fe2O3, CaO, Na2O and K2O are converted into a molecular proportion by dividing weight percent oxide by the molecular weight of the oxides. Second, in albite, the molecular ratio Na2O, Al2O3 is 1:1. Similarly, in potash feldspar, the molecular ratio K2O and Al2O3 is also 1:1. Therefore, the molecular proportion of Na2O and K2O are added, that is Na2O plus K2O, and an equal amount to their sum is subtracted from the molecular proportion of Al2O3 plus Fe2O3, that is the Al2O3 plus Fe2O3 minus under bracket Na2O plus K2O. Third, A plus C plus F can now be written as A equal to Al2O3 plus Fe2O3 minus under bracket Na2O plus K2O, C equal to CaO minus 3.3 into P2O5, F equal to FeO plus MgO plus MnO. For the purpose of graphic presentation, these values are recalculated so that A plus C plus F equal to 100, that is, they are expressed as a molecular percentage. On the ACF diagram, the observed minerals phases in the different rocks, within exception of the quartz, albite, orthoclase, are plotted using their chemical formula. The chemical formula is based on molecular proportion, that is possible to divide the three components diagram into a triangular field such that only rocks whose chemical composition fall within a given triangle will be found to consist of the three minerals phases located at apex of that triangle. If the chemical composition of a rock lie along the join of two minerals, only two phases are expected to be present in the rock. Thus, in the three component system, number of phases commonly do not exceed 3. This is the main application of a mineralogical phase rule. By creating these three pseudo components, Ascola reduced the number of components in the mafic rocks from 8 to 3. Water is omitted and assumed to be mobile. SiO2 is simply ignored, equivalent to projecting from quartz. In order for a projected phase diagram to be truly valid, the phase from which it is projected must be present in the mineral assemblages. Represented a typical ACF compatibility diagram referring to a specific range of P and T. The kyanite zone of Green's phases now take up how to calculate the ACF values of some common minerals. For example, the talc, the chemical formula is Mg3 Si4 O10 OS twice. If during calculation we can see as per the formula of talc, there is no A, no C, only F is present, that is F equal to thrice MgO. Therefore, the value of A equal to 0, C equal to 0, F equal to 100%. Second, anthophyllite or cummingtonite, the formula is under bracket MgFe7 Si8O22 OS twice. During calculation, we can see F component is present, A and C is equal to 0. Therefore, we can, during calculation, we can see the value of A equal to 0, C equal to 0 and F equal to 100%. Hypersthene, the formula is Mg Fe twice Si2O6. The value of the A equal to 0, F equal to 100% and C equal to 0. Therefore, the plot will be exact on F corner. Dolomite, CaMg under bracket CO3 calcium carbonate twice. Therefore, the value of A equal to 0, C equal to 50%, F equal to 50%. Diopside, the chemical formula is calcium magnesium Si2O6. Therefore, the value of A equal to 0, C equal to 50% and F equal to 50%. The calcite chemical formula is CaCO3. The value of A equal to 0, F equal to 0 and therefore, the C equal to 100%. Now, the next mineral is tremolite oblique actinolite. The formula is Ca2 under bracket Mg, Fe 5 Si8O22 OS twice. Here the value of A, C and F equal to A equal to 0, C equal to 29 and F equal to 71. The next mineral is vesuvinite. The chemical formula is 10 CaO, 2 MgO, 2 Al2O3, 9 SiO2 and 2 S2O. Therefore, the value of C equal to 72, A equal to 14 and F equal to 14. Epidote, the chemical formula is 4 CaO, 3 under bracket Al, Fe plus 3 bracket closed twice O thrice 6 SiO2, 2 S2O. The value of A equal to 43, C equal to 57 and F equal to 0. The next formula is pyrophyllite. The chemical formula of pyrophyllite is Al2 Si4 O10 OS twice. Therefore, the value of A equal to 100% because in pyrophyllite there is no Fe, FeO or MgO or CO. The next formula is your kyanite oblique sillimanite or andalusite. The chemical formula is Al2 SiO5 where the value of A equal to 100% and C and F equal to 00. Sterlite, the chemical formula of sterlite is 2 Al2O3, FeO, 2 SiO2 and S2O. A equal to 67% and F equal to 33% and C equal to 0. Chloritoid, FeO, Al2O3, SiO2, S2O. Therefore, A equal to 50%, F equal to 50% and C equal to 0. Now, the next formula is almandine Fe2 Al3 Si3 O12. The value of A equal to 25, F equal to 75%. Cordierite 2 Mg Fe plus 2 O, 2 Al2 O3 and SiO2. The value of F equal to 50 and A equal to 50 and C equal to 0. The next formula is wollastonite. The chemical formula of wollastonite is CaSiO thrice. The value of C equal to 100% and A and F equal to 00. The next is anorthite CaAl2 Si2O8, A equal to 50%, C equal to 50% and F equal to 0 because in anorthite there is no FeO or MgO present. The next formula is lomentite CaAl2 Si4 O12 4S2O, A equal to 50 and C equal to 50 and F equal to 0. Lawsonite CaAl2 Si2 O7 OS twice and 4S2O. Therefore, the value of A equal to 50, C equal to 50 and F equal to 0%. Chloride always show variable composition. Value of F varies from 90 to 65% and A equal to 10 to 35%. The chemical formula is Mg5 under bracket Mg comma Al bracket close, another bracket Al comma Si bracket close, Si3O10 OH8 up to Mg Fe4 Al2 under bracket Al2 Si2O10 and OH8 hornblende contains, in contrast to tremolite variables, amount of Al2O3 and MgFeO. Their CO component varies somewhat as well. Therefore, the composition of various hornblende must be shown by an elongated field on the ACF diagram extending from the point representing tremolite towards the A corner. Similarly, biotite extend from F corner to about A equal to 18, F equal to 82. In this modules, I have discussed about the graphical representation of minerals assemblages. I have covered the whole topic under the following heads: the phase rule, simplifying degree of freedom, simplifying components, metamorphic phase diagrams, ACF diagrams, method of calculation, AKF diagram, AFM projection, the most commonly used chemographic diagrams are the ACF, AKF, AFM, A dash, F dash, M dash and CO, MGO, SiO2 diagrams. These chemographic diagrams are graphical description of phases, composition and coexisting phases relationship. Most are triangular diagram that show a particular metamorphic grade or a limit pressure temperature range. When a diagram reveals an anomaly such as crossing the tie line, the reason can generally be found by turning to a mode system C more than 3 and the original Gibbs phase rule.